Hello, I'm Liam Hoover. I'm a senior robotics student here at Embry-Riddle Aeronautical University, and this is my PLC project.
And I'm Kira McGarry. I'm also a senior robotics student at Embry-Riddle.
Okay, so here we are going to move into our second amazing PLC project.
Here we have our motor that will drive our belt. These are our pneumatic cylinders. Right now we are only using, these are our solenoids for our pneumatic cylinder. At the moment we are only using this fourth one. And this is an inductive sensor to determine whether an object is metallic or not.
Okay, so do you want to show us the system in practice?
Yeah.
You want to run the HMI and get it done?
Yeah.
And then we go over your PLC program. Go ahead.
So to turn on the system, the enable for the stepper motor and all other systems are on this toggle switch for safety. We have a analog input, which is our potentiometer that controls how far the belt will move. These buttons 1 and 2 control the forward motion and the backward motion of the belt in a jogging state, I guess. And then number 3 will run the belt at a set distance based on the potentiometer.
Okay, so once we hit this switch to enable the system, it will activate the sorter. The way that it works is that the stepper driver will move the conveyor belt. This cardboard box will not be detected by the sensor. This metal box will, so once it hits under the sensor, it will be pushed off of the system. And once we hit 3,
So here we have an inductive sensor which can only detect metals, but we also have a capacitive proximity sensor which we can replace, and in that case we can detect and basically eject any type of object. So this is the physical system, this is their HMI and the controls, and here is the actual PLC logic. So I zoom in so Liam can briefly tell us about what he has over here.
Yeah. So this first network block, this is to make our motor move. The NC power is what enables our motor. Then we have 2 other ways of moving our motor. We have a jog movement, which is on buttons 1 and 2. This will jog the motor at a set velocity of 200 millimeters per second. And then we have a relative move for the motor. This will move the motor in one direction when it is activated on button 3, and the distance is determined by the scaled potentiometer. The scaled potentiometer is the scaled potentiometer comes from the user input turning the potentiometer knob. Then it normalizes that between our minimum voltage and our maximum voltage. Then it scales it between 1 and 5,000, which is moving 100 millimeters and moving 5,000 millimeters. This then goes to scaled pot, which is our moving distance, which is used in this relative move. To make the pneumatic move, we have the capacitive touch as a input. Then it goes into a timer, which will delay the output of the pneumatic by 500 milliseconds, so half a second. Next, we have a counter. This is for the HMI. The counter runs off of test valve, which is our pneumatic. So every time the pneumatic is fired, it increases the count, and the count is also reset by button 4.
Okay, thank you so much, Liam. Thank you so much, Kira. So again, this is our belt system and ejection of metal objects, which can be extended to any objects. All system is done here with one Siemens package, educational package, which is the brain, the HMI communication module, and the power supply, and some extra electronics that they had to buy, and pneumatic systems. So if you just want to give us a rough estimate of how much the electronics and anything besides the Siemens system costs, would you say what, below 500? Or
I would say the electronics would be below 500. I'm not too sure about the aluminum,
okay,
but you could build this below 500 easily.
but the whole system could probably, if you consider the Siemens system at the $1,000, The rest of it could be done also at about $1,000, no more,
Oh,
right?
yeah,
So
for sure.
$2,000 at most, the cost of this system. And you know that if you want to get a system like this, a demo panel, the cost of buying it from a vendor is well above $10,000. So this is the value added by our senior robotics students working on their semester-long PLC projects. Thank you so much. This is a great job. Thank you. One other thing that just worth mentioning before we finish this video is even the belt here is 3D printed from flexible plastic TPU. So as you can see, everything here started from very, very small components, and our students either made them, all of this frame also made from our aluminum profiles that we had without use, and so they really started from scratch and put everything together, or they made it. As you can see, lots of parts are 3D printed here. So hopefully it was useful to you. I'll see you in the next lecture. Thank you.